NMR. So NMR stands for, N stands for nuclear, M stands for magnetic, R stands for resonance. So it is nuclear magnetic resonance. So you already learned something about spectroscopy. What is spectroscopy? Anybody? Okay, it's almost one way. Okay, fine. So spectroscopy means it is an important branch of science that deals with the interaction between matter and energy. So after interacting electromagnetic radiation with matter, what happens? So separation takes place. So due to the separation, we want to detect something. So that detection involves recording the energy changes. That we call it as a response peaks. Okay, response peaks. So energy changes that can be recorded. So that is a very useful in order to study the structure, in order to study the bonding length, in order to study the bond angle. Okay. So all these informations. So you are going to get almost accurate informations. So using spectroscopy only. That is why spectroscopy is a very, very important subject. So without spectroscopy, it's very difficult to imagine. Okay. So there are various types of types. One is so the spectrum due to the atoms. Okay. Interaction, electromagnetic interaction between the atoms. Okay. Between the molecules, between the electrons. Likewise, between the nucleus. What is this? It is the electromagnetic interaction of electromagnetic radiation with nucleus. So nucleus. So not all the nucleus or not all the nuclei is capable of giving such kind of responses to NMR. Why? Because only you have to follow this sentence very carefully. Okay. So only the nuclei with odd number of protons or odd number of neutrons or even number of neutrons, they are capable of giving NMR. They are capable of giving NMR. So I am going to call it as only the nuclei with odd number of protons and even or odd number of neutrons. So they are capable of giving or producing NMR spectrums. Okay. So totally I am going to call it as NMR active. Only such nuclei are NMR active. Okay. So now, so how exactly we are going to get NMR? I am going to give in a very simple way. Okay. So why? What is the reason for this? So suppose you consider the nucleus. Okay. So I start with the proton. Okay. I start with proton. So okay. So that is 1H1. So the hydrogen contains only one proton, one electron, no neutron. Okay. In this particular case. So therefore, this is capable of giving NMR. What is the reason why it gives NMR? That is an important question. It gives NMR because, so like your electron, it is also a charged particle. Which one? Nucleus. Due to the presence of positive charge, what happens? Any charged particle which is spinning like this, okay, so or like this. So it may be spin in the clockwise. So that is plus half. If the spins in the anti-clockwise, then we are going to represent by minus half. Okay. So now, any charged particle, suppose it is moving around its own axis. What happens? So it already generates spin angular momentum. So automatically it possesses spin angular momentum. So spin angular momentum in turn produces magnetic dipole. So magnetic dipole means, once again, the nucleus acts as a teeny bar magnet, small bar magnet. So I'm going to call it as a teeny bar magnet. So you see, so any charged particle, suppose it is moving around its own axis, what happens? Automatically it poses spin angular momentum. Not only in this case, even it is true in electron also. Okay, so that is negatively charged, that is moving around its own axis. Okay, maybe clockwise. Okay, so the spin is upwards. Maybe anti-clockwise, the spin is downwards. Okay, so such kind of particles always produces. Okay. ಇನ್ನೂ ಬರ್ತಾನೆ ಇದ್ದೀರಿ ಅಡ್ಮಿಟ್ ಸೊ ಯಾಕೆ ಇಷ್ಟು ಲೇಟು ವೈ what is the reason sir so this is a very simple in this particular case what happens I am talking about NMR. N stands for nuclear magnetic resonance. So this is totally the interaction between nucleus and electromagnetic radiation. Not all the electromagnetic regions are capable of giving NMR. Okay, not capable of giving NMR. Only the radio frequency waves. Only the radio waves they are capable of giving NMR. Only the energy of that particular wave is very less. Okay. Okay. So NMR is a very important subject. Why it is very important? Like your UV spectroscopy, visible spectroscopy, infrared ray spectroscopy. This is also very important and very good spectroscopy, NMR spectroscopy. So like your UV or infrared or visible spectroscopy, it is also a very good spectroscopy. Why it is very good? Because it needs only the small sample. It needs only the small sample. And after the your testing, after the analysis, what happens? We can easily recover the sample and reuse the same sample for several times. So why NMR is very advantage? Because whatever the sample it needs, only in a small quantity. So what is such difficulty in getting small samples? So especially in natural products, especially in some photochemical reactions. So this NMR is very useful to study the natural products, to study some photochemical reactions. In such a case, getting the sample is itself a very difficult. Therefore, so we need only it is possible to get only small samples. So that much is enough to carry out NMR analysis. That much sample is enough to carry out NMR analysis. So I am going to give you another important. This is advantages. These are the advantages. It is very useful to study the natural products and as well as some photochemical reactions. Not only that, even nowadays the NMR is improved like anything. So nowadays, ನೀವೇನು ಹಾಸ್ಪಿಟಲ್ಗಳಲ್ಲಿ ಹೋಗ್ತಿರಲ್ರಿ MRI ಸ್ಕ್ಯಾನಿಂಗ್, ವಾಟ್ ವಿ ಕಾಲ್ ಇಟ್ ಆಸ್ MRI ಸ್ಕ್ಯಾನಿಂಗ್, ಸಿಟಿ ಸ್ಕ್ಯಾನಿಂಗ್ ಏನಂತಿರಲ್ಲ ನೀವು. ಸೊ ಯು ಟೋಟಲಿ ಸೊ ದಿಸ್ ಈಸ್ ದಿ ಕಾಂಟ್ರಿಬ್ಯೂಷನ್ ಆಫ್ ಯುವರ್ NMR. ಓಕೆ, ಸೊ ಯುವರ್ MRI images are due to your NMR. So in such a way, the contribution of NMR is very okay, highly appreciable. Okay, fine. So now I am talking about it is the interaction between the nucleus with electromagnetic, especially the radio frequency waves, Okay, only the energy of such waves are very less, and we need a very small quantity of sample. Okay, that is also okay, and we can reuse the same sample for several times. Okay, so that is another advantage. So it is very useful to study the natural products as well as photochemical reactions. Okay, that is okay. Now, what about the other term, NMR? I told you NMR. This is okay. Nuclear.
Magnetic resonance.
This is okay. Magnetic. What about this resonance? So nuclear, I told only the nuclei with odd number of protons and odd number of neutrons, okay, or even number of neutrons is also okay. So now we already see protons are positively charged particles, even electrons they are electrically neutral. So, but actually they have also have partial charges, okay, partial charges. Even neutron is also behaves like a charged particle, and it also produces magnetic field in this instance. So don't worry about all those things. Okay, now I am talking about nucleus contains protons, that is positively charged. Okay, so and electrically neutral neutrons. So only the nuclei with odd number of protons and odd number of neutrons, that also capable of giving NMR. So that is I am going to call it as NMR active. Similarly, odd number of protons and even number of neutrons also NMR active. NMR active. Okay, that is okay. Nucleus is concerned. So what is this magnetic field? So it is the applied magnetic field. It is the external field applied between the nucleus. Suppose this is the nucleus. So this is the applied field. So what is this? This is sound. So usually you are all studied all these things in physics. Okay. Now, so usually force of lines, magnetic force of lines starts from north end to south end. Okay, starts from north end, terminates at south end. So similarly, what happens? They same. Similarly, same. Okay. So now this is the nucleus. Okay. Once again, I am not ready to repeat the same old dialogue. Okay. So this is the nucleus. Okay. This interacts with electromagnetic radiation, especially radio waves. Okay. This is radio wave. Radio waves. Okay. RW, radio waves. So if this radiation is capable of reacting with this nucleus, then we call it as such interactions, we call it as a resonance. Resonance. When it is possible, okay, this is the magnetic field kept around the nucleus. Okay. Now your nucleus is also acts as a magnet. Okay, also acts as a magnet because it has a positive charge. It has a positive charge and it is spinning like this. So due to the continuous spinning, what happens? It possesses spin angular momentum. What is spin angular momentum? So I am going to call it as a P. So now whatever I am talking, so it is another important 4-mark question. What is that question? Explain the principle involved in NMR. So it is an important 4-mark question. What is the question? Explain the principle involved in NMR spectroscopy. So how we will start? So you have to start your answer from this. So nuclei with odd number of protons or odd or even number of neutrons, they are all NMR active. Okay. So due to the presence of positive charge on proton and it is spinning. Okay. If it is plus up, so that spins in the clockwise. If it is minus up, that spins in the anti-clockwise. So such type of continuous motion, the same nucleus possesses spin angular momentum. What is the spin angular momentum? I know in some textbook it is indicated by I. In some textbook it is designated or represented as P. Okay. P is equal to h by 2 by square root of I into I plus 1. So what is this? Spin angular momentum. So what is this? Spin angular momentum. So this spin angular momentum in nucleus, what happens? Automatically it produces magnetic dipole. Your nucleus, this is your nucleus. This acts as a teeny bar magnet. Okay. So it produces positive and at one side and negative one side. No, I am not going to consider positive negative. I'm going to consider north pole. It follows dipole. One is north pole at one end, south pole at another. So once again, so it also considered as the same magnetic. It also produces magnetic. It starts from north end to south end. North end to south end. Like this. So totally I'm going to call it as it also behaves like a teeny ball magnet. Okay. So what is the magnetic strength of this? That is represented by the symbol. Okay. I'm going to give all these things in a very simple. So any charged particle, okay, so moving around and about its own axis, what happens? It produces spin angular momentum, that is P or I, whatever you call. Okay, so that is equal to h by 2 by square root of I into I plus 1. Okay, I into I plus 1. Okay, so this is where I is, what is I? Spin quantum number. So the remaining h is Planck constant, pi is constant. Okay, remaining everything is known. So due to the spin angular momentum, what happens? So that produces, that generates, that forms, okay, magnetic dipole. I told you now. So at one side it forms north pole, another side it forms south. So okay, that also acts as a, so the nucleus acts as a small ball magnet. So the magnetic strength of that magnet I am going to represent by mu n, that is equal to, so that mu n, okay, so G Q, okay, that is GQH H by 4 pi m into square root of I into I plus 1. So much. First one I am going to call equation number 1. The second one, so much joules per Tesla. Okay, I am going to write as equation number 2. So the magnetic strength of the magnetic dipole, the strength of the magnetic dipole, that is given by the symbol mu n, that is equal to GQH divided by 4 pi m. Here also I is once again spin quantum number. What is
quantum number?
Okay.
Acceleration due to gravity.
Very good. So Q charge of the proton. So similarly M mass of the proton. So all these things. Suppose I am going to represent this M by the symbol capital M and the charge Q I am going to represent from the symbol PE. So the equation 2 becomes once again what happens? So that mu n, that is equal to G Q H divided by this 2 becomes PE. So P being the number of protons, P being the number of protons. So GPH by 4 by capital M, small m becomes capital M. So the remaining is as it is. What is this? I into I plus 1. So much joule per Tesla. This is equation number 3. Okay, once again. So now, any nuclear dipoles are conveniently expressed in terms of nuclear magneton, that is beta n. So any magnetic strength, so conveniently expressed in terms of beta n. Beta n is equal to EH, once again, 4 pi MP. So it is always equal to 5.05 into 10 to the power minus 27. So much. Joule per Tesla. So the magnetic strength is generally expressed in terms of nuclear magneton. So that is So beta n is equal to EH by 4 pi mp. Same charge, everything is same, mass of the proton, everything is same. It is always equivalent to 5.05 into 10 to the power minus 27 joule per Tesla. If I consider the same thing, in equation number 3, equation 3 becomes, what happens to equation 3? That becomes mu n is equal to, what happens? Gp mp divided by Gp mp divided by 4 pi mp divided by capital M into beta n.
Sir, cancel sir.
Hello? Oh, ಅದು ಆ ಕಡೆ ಕಾಣಿಸಲ್ಲ ಅಲ್ವಾ? Oh, sorry.
Yes, sir.
ಕಾಣಿಸಲ್ಲ ಅಲ್ವಾ?
Cancel sir.
Okay, if I consider, ಕಾಣಿಸುತ್ತಾ ಆ ಕಡೆ? Okay.
ಇಲ್ಲ sir.
Okay, if I consider the same nuclear magneton in equation number 3, what happens? Equation 3 becomes, okay. Equation 3 becomes, so mu n, strength of the magnetic dipole, mu n, that is equal to Gp, okay, mass of the proton mp divided by capital M, okay, beta n into square root of I into, this is I into I plus 1, so much joule per Tesla. So I am going to call equation number 4. Okay. So equation 4. But Gp mp divided by m, that is equal to Gn. What is this? Gp mp by n. Gp mp by m. So this is nothing but Gn. So this is also called as nuclear splitting factor. Okay. So this is, if I consider the same thing, if I rewrite the equation 4, equation becomes mu n is equal to Gn, okay, so beta n into I plus 1, so much joule per Tesla. So this is the equation. Okay, this is the magnetic strength of the nucleus. Where is your nucleus? It is here. Can you able to see it? Okay, I'm going to write say nucleus here. Okay, this is south pole. This is north pole. Sorry, this is north pole. This is south pole. This is the external magnetic field. So somebody wants to join. Why? Now this is the strength of the magnet. Gn beta n into I plus 1. Okay. Where is this? This is the nucleus. So this is the strength of this nucleus. Nuclei or nucleus. Any nucleus with odd number of protons or odd number of neutrons or even number of neutrons. Even of 5 neutrons. Okay. That also NMR active. Okay, fine. If you keep, this is the strength of the magnetic field. Okay, nucleus. Again, I am going to write this is another magnet. It is kept inside one more magnetic field. This is another magnetic field. Okay. So now what happens to this? Suppose I am going to keep this magnet in presence of another magnetic field. What happens? So that is in presence of with respect to that magnetic direction. Okay. The magnetic field direction starts from, so here north to the south. This is the direction of the magnetic field, applied magnetic field. So this is the direction of the applied magnetic field. Okay, fine. Okay, now suppose I is equal to R. Totally I am going to write as the same. The strength of the magnetic field with respect to the applied magnetic field, this becomes mu z, that is equal to Gn beta n, okay, into Bz. This is the strength of the applied magnetic field multiplied by Iz. So Iz can take either half, plus half or minus half. Okay. else do you expect according to quantum mechanics? There are the allowed energy levels. The allowed energy levels is nothing but 2i plus 1 levels. So if suppose I substitute instead of I am going to substitute half. What happens? 2 to get cancels. So 1 plus 1, there are 2 energy levels. 2 energy, nuclear energy levels. Okay. So now, so what are those 2 energy levels? Okay, suppose the spin of this nucleus is like this. So what I am going to call it as plus half. Suppose the spin of this particular nucleus is like this. So I am going to call it as minus half. So what happens here? So this is against to, you see, the magnetic field direction. The applied magnetic field direction is like this. But the magnetic field direction, or suppose this is minus half. It need not be the plus half or minus half. This is our only the convention. Okay, suppose this is plus half. Now this is along, this aligns, or this is according to the applied magnetic field, but it is against to the applied magnetic field. Therefore, this is the axis of the magnetic field. This is the energy level, nuclear energy level. Okay, so this is opposing the applied magnetic field. Therefore, what happens? So you are going to get this energy level. I am going to call this is minus half. Similarly, what happens? The same nucleus. Okay, so it is with the applied magnetic field. Therefore, it comes back to lower energy level. What is this? Plus half. So now what I am going to call it here, the gap between these two columns, delta E. The gap between these two energy levels, we call it as a delta E. So this delta E, okay, that is equal to this much. What is this? Gn, okay. This delta is always equal to h nu, or I am going to call simply nu, that is equal to this much of energy Gn, beta N, Bz divided by h. Okay. So I am going to call this is the, whenever you are passing your radio waves towards the nucleus, that radio frequency waves is exactly equal to this much. So what happens? Your nucleus starts responding. So that gives that starts absorbing that radiations, radio frequency waves. So that we call it as a resonance. That we call it as a third name of resonance, NMR. Right? We call it as a resonance. Then only we are going to get signals, NMR signals. Okay. So now, so any doubt about this? Hello? And even odd number of or even number of neutrons. So that is NMR active. Okay. Athara nucleus, if you keep in presence of any applied magnetic field, adu interact agak shuru agutte because it is one magnet that another magnet, the interaction between two magnetic fields. So ee eradu magnetic field interaction ge adenagutte energy levels, two different energy levels create agute. Ive nodidre ಒಂದು higher energy level, adana higher energy level is always called alpha state, a lower energy level is also called as beta state. Okay, so that gap we call it as a delta E. Okay, ಆ ತರ ಎರಡು ಎನರ್ಜಿ ಲೆವೆಲ್ ಆಯ್ತು. ಇವಾಗ ನಿಮ್ಮ ನ್ಯೂಕ್ಲಿಯಸ್ ಇವಾಗ ಈ ಎನರ್ಜಿ ಲೆವೆಲ್ ಇದೆ. ಸಪೋಸ್ ಇವಾಗ ನ್ಯೂಕ್ಲಿಯಸ್ is this particular energy level. You continuously you are passing your radio waves towards this nucleus. Okay, towards this nucleus. Okay, you are passing towards the nucleus. So when it is going to absorb, only this frequency is equal to this frequency. Okay, only this frequency of this, there is that frequency, this is the frequency. When this frequency is exactly equal to nu, so the frequency of the electromagnetic radiation, it starts absorbing the radiations. So absorb ಮಾಡ್ಕೊಂಡು ಅಷ್ಟೇ ಏನಾಗುತ್ತೆ, that flips. So that jumps from this energy level to this energy level. ಈ energy level ಇಂದ ಈ energy level jump ಆದ್ರೆ ಏನಾಗುತ್ತೆ? Suppose I am producing, okay, so I am producing this radio waves through a coil. current only where the nucleus jump from this energy level to this energy level, what happens? The change in the magnetic legs. So that is connected with conductor. Coil is a conductor. So then what happens? That automatically produces EMF. ಆ EMF ಏನಾಗುತ್ತೆ? ಡಿಟೆಕ್ಟ್ ಇಂದ ರೆಕಾರ್ಡ್ ಗೆ ಹೋಗುತ್ತೆ. That will record it in the record. Very simple. So any doubt? ಅವರು ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್ ಬರ್ಬೋದು ಪ್ರಾಬಬಲಿ.